I really do think being able to do this will make your life better. Right? Yeah? The answer is, what this says is that P is uncomputable, and whether it's true or false depends on whether P is computable or not. Right? And if you said that because you didn't notice at the very top it said P was computable, I would give you full marks, right? Because you got what we needed, right? All right. So one of the things that I do when I teach 2001, and in fact, if you like me, I'm teaching 2001 next year, is Turing machines are an ugly model of computation, right? They're ugly. And most professors, they teach it by making you write code in a Turing machine, which to me is just painful, right? What do I want to know? What do I want you to get out of Turing machines is the fact that we're in a state and we transition between states, and that I can take a Java program. You give me a Java program, I can compile it into a Turing machine, right? And we could go the other way. You give me a Turing machine, I can find a Java. That seems more obvious, right? Java programs, Turing machines are pretty straightforward. Can you write a Java program to simulate this Turing machine? Absolutely, right? Given an arbitrary Java program, can you write a Turing machine that does it, right? It's one thing that I cover. And there are two things that you need to know to do that. One, you need to know what a Turing machine is, right? Am I going to teach you what a Turing machine is today? No, right? That's next term. But you need to be able to play the game, right? And so what we're doing today is playing the game. All right. He defines Turing machines, right? What is a Turing machine? You're in a state, and you have a head looking at an infinite tape. You move the head. All you know, what does the machine know? It knows what state you're in and the character you're looking at where the head is. And based on that, it changes its state, and it moves its head left, writes something on the tape, moves left and right. That's a Turing machine, right? So here's the statement. There exists given a problem P, right? Now what are we saying? Yeah, I mean, everybody translate this. What does this say? Yeah, but you can start dropping things, right? It's really only saying something about P. P is our free variable, right? So what are we saying about P? I mean, let's roll it back. If you get rid of the machine, what is it saying? If M is a Turing machine, it's saying M solves P, right? If you get rid of the I, it says M solves P on I. If you bring this in, M solves P. If you bring this in, oh, M's a Turing machine. P is computed by a Turing machine, right? There's the set of all computational problems computable by a Turing machine, right? Turing defined computable by defining a Turing machine, right? Now, what does this say? It say P is computable by a Java program, right? Right? Oh, I went to a mountain with this woman who wanted to climb it, and my empowerment statement was, I can do anything she can do, but not as well, right? So it was 5 CN towers up. And I got to the top, but she was way ahead of me. All right, so here's, if a Turing machine can do it, a Java program can do it, right? If a Java program can do it, a Turing machine can do it. What we're saying is these are equivalent. The set of problems you can solve by a Java program and the set you can solve by a Turing machine are the same, right? You can compile back and forth, right? All right, so running time matters, right? So here I'm saying, right? I'm just adding the same is how much time it takes, right? We're not even saying how long it is. We're just saying there's some running time, all right? And partly I'm doing it because when we translate back and forth, we're going to translate, there's going to be a blow up in time, right? Everybody good? All right. Right, so the Turing machine must be fixed before the input's known, right? When you give me the input, there's a running time that depends on the input, right? Computational problem A, what does A say? Computational problem P is solved by a Turing machine, or by a Turing machine, right? By a Turing machine, Java program or a Turing machine, right? And what, right? So we want to prove that A gives me Z, right? Now, what do we need? We need other statements. We need to say Java programs, which way are we going here? If it can if it can be done by a Java program, then it can be done by a Turing machine. Why? Because you give me a Java program, I can simulate it, right? How do we say? You should be able to write down in first order logic how you say Java programs can be simulated, right? And what's the time? Well, the Turing machine, if the Java time takes time t, Turing machine takes time t squared, right? So, and here we want to say computational problem P treats inputs that are in binary and ASCII the same. All right? We've got to do these very statements. All right. So we didn't write these down, but we're going to have to write those down. All right. So let's go here. What does this say? Oh, here. It says Turing machine takes the input in binary, right? And given something in binary, I can translate it over to ASCII, right? And there's a function that maps, let's call it B, that takes as input something in binary and maps it over to something in ASCII, right? People we're just saying things that we know, right? So here, you give me a binary, it gives me an ASCII, right? Problem, right? What it says is P, if you give it something in binary and you give it something in ASCII, it doesn't care, right? So here I'm saying P gives the same answer in binary and ASCII. And what are we saying? For every binary you translate it over to ASCII, the problem is going to, is it too loud? It's a little, okay, right? We translate it over to ASCII, it does the same, right? Everybody see what we're doing here? I'm just throwing in fun things that we know in computer science, right? In fact, in computer science, we'll say, over here could be a graph, and here could be a representation of the graph in binary, and we do the same, right? These are things that we just assume are true, right? The problem takes a graph as input. Well, how does it do it? Well, really, it takes it in binary. All right, so here we have another thing. You give me a Java program, I compile it, into a Turing machine, right? So this works like a compiler. It translates code into, right? You give it a Java program, the compiler treats it into machine code, but we convert it into a Turing machine, right? So we're saying Java programs can be converted into Turing machines, right? Which Java programs? Right? We want to say all Java programs can be simulated by a Turing machine, right? What does that mean? What does simulated mean? Well, M prime simulates M if it gives the same answers, right? So which Turing machine? Some Turing machine, right? What are we missing? We got to say inputs, all inputs, right? So we got it written down here. How do we denote this? Right? Here. So you should be able to get this. Am I losing people? Right? Here I'm saying every Java program. You give me a Java program. What am I going to do with it? I'm going to look at your Java program and I'm going to compile it into a Turing machine, right? For every Java program, and it's a proof by construction. One thing I'm adding to the last question on that assignment was that proof by construction means that if you say there exists something, then you have an algorithm to construct it, right? So this says for every Java program, you give me a Java program, I can compile it into a Turing machine, right? Such that what? Such that for any input, they give the same answer, right? Everybody buy that? Right? And takes the square, right? Takes the square of the time, right? So how much time? If the Java program takes time t, then the Turing machine takes time t squared, right? For all times, right? Here we're going to say, and, here I got an and here, and for all times, if the Java program takes time t, then the Turing machine takes time t squared, right? Everybody kind of good? All right. So those are all our sentences, right? Make sure you understand them and right? I mean, I think this could be on an exam question, right? It's a little long, right? But what do we want to prove? That A, B, and C gives me Z, right? How many of you think you could write down a proof that A, B, and C gives me Z? None of you. All right? With enough time. All right? All right. So let's prove it. All right? Let's just bang it out. Right? So I'm going to try how much time do we got? 3 minutes? Oh, I was going to go slowly. I'm not going to go slowly. All right? We're going to get it done in 3 minutes. Let's just bang it out, okay? Don't turn on your brain. Everybody turn your brain off and see if you can just bang this out, all right? So I'm trying to prove this. So what do I have? I have to construct a Turing machine, right? I'm playing the game. Oh, I must construct a Turing machine. Do I know how to construct Turing machines? Right, this is just saying the game, right? Why? Because I'm going to use these slides in 2001, and they don't know the game. All right? All right, so I need to construct it, right? And then I'm going to be given this by my adversary, right? And then I got to construct the time, right? And then I have to prove that it solves the problem, and then I have to prove what the running time is, right? This is what you have to do, right? So you write these down either on your scrap paper or you just fill them in various places on the actual paper because you know you're going to need them, right? What does this one do? This one, we're going to assume A is true, right? And if A is true, for every Java, there exists a Java program. It's for all inputs I and times T. This is the one for the Java programs, right? It says Java programs, P can be solved by a Java program, right? So you go to the Oracle. The Oracle is saying P can be solved by a Java program. What does it do? It gives you, she gives you a Java program, right? So, right, let M be the Java program that the Oracle assures us it exists, right? And then I is the prover can give her an input, right? I give her an input. And what does she do? She gives me on that input what the, yeah? Sorry, what? Oh, because our goal is to assume A, B, and C are true and to prove Z, right? That's the statement. So we started by assuming, right? Right? We're told that P is computable by a Java program, and we have to prove that it's computable by a Turing machine. Good question, right? Everybody get that? We're running out of time, but I mean, let's just go through here, right? What's this game? She assures us that P is computable by a Java program. She gives us a Java program. We give her an input. She gives us the running time. And yes, it solves the problem in the right amount of time, right? It's a very useful oracle, right? Everybody get her? Right? What does this guy do? This is back to a Turing machine, right? All right, so now, this is just our converter, right? We're going to convert our guy, right? What does this guy say? It says, for all, it's an oracle. You give her a string in binary, and she will convert it over to a string in ASCII and assure you that the answer for the problem is the same, right? Not that useful. I mean, useful, but what does this one say? Says that we can compile. It says, if you give me a Java program, I can compile it into a Turing machine that's that on all inputs, they give the right answer, right? And the running time is squared, right? I mean, I hope all you're saying, well, of course, if I have A, B, and C, then I have Z, right? I'm hoping you're, right?
The A was the converter for the binary, so for Z, whatever your binary input, that you can change it up to ASCII. Right?
Yeah, I mean, we don't have much time here, right? So I'm going to just read it out and see if you can follow it, right? Here, I'm trying to prove that there exists a Turing. We have a problem P, and I'm trying to prove that there exists a Turing machine that solves it, right? So how do I come up with a Turing machine? That's a big statement. Well, who gives me something? A gives me a Java program, right? What do I do with that Java program? Oh, I give that Java program to C. What does C do? She gives me a Turing machine, right? Oh, here, I can push the buttons, right? Right? We got a line of where we are, right? I get a Java program. What do I do with it? I give it to C. What does C do? C gives me a Turing machine. Great. How did it do it? It compiled. Right? All right. So now this is where we are. I have it, right? We've moved up to those lines. Everybody see that? So what am I doing? I'm now given a binary string, right? What do I do with my binary string? I give it to B. What does B do for me? B converts it into an ASCII and assures me that the answer is the same, right? All right. Now, what do I do with the ASCII? I give A the ASCII, right? And what does A do? Well, let's go back to right? Oh, I give A the ASCII, and she shows that it works. I don't know. Here, right here. What do I do with my ASCII? I'm going to give my ASCII to this, right? Those two people, right? Right. And then how do I construct the time here? Right. Well, I gave this guy an ASCII, and she gave me the running time. Right. How do I go from A's running time to my running time? Remember, I square it. Right. My running time is the square. Right. And so then now I have to prove that this is true. Right. How do I prove it's true? Well, I know that the Java program works. I know that the problem is the same on ASCII, right? And so, and I know, right? I know these various, right? And I put them together. Everybody good? All right. Look at that yourself. Have a great weekend. How many? Wait. Course reviews are out. And I've been told by the department that I'm supposed to really push people to do them. Partly because, I teach this course in a very different way than George does. So I would love it if you told us your opinion. Another thing I want you to say is they've been talking about dropping this course from the curriculum. And what I say is George's course isn't useful, and I believe mine is useful. So you got to decide what you believe about it and do course evaluations.